Hey, this is Voxide, and if you want to learn Houdini, you can check out my in-depth courses. Link will be in the description. So I want to run over a few cases and a few examples of how to fix particle stepping, and what I often see is people just straight away start to increase the subsamples to fix stepping, and this is not what you want. You only want to increase the substeps only as a last resort. So usually in my projects I hardly ever go higher than one substep, and at most I will use 2 or 3 substeps, and if I really need more substeps than 3, for example, then it's really a problem with the setup. So things we do either inside the pop simulation or before the pop simulation that causes the ugly stepping. So let's just set up some few examples and I will run over all of the cases that I can think of. So let's maybe just start fresh and I'll use a sphere. So let's just drop a sphere in the middle of my scene. I will set this to be polygon and maybe I'll just increase the geometry, so the frequency, and let's drop a transform. And I'll set this to be 5 on the Y, so I just want to translate it a little bit, and we'll use a second transform which we can then use to animate this around the center with this Y value here. So I will set this rotate value to be $F, and I will maybe, let's multiply this by 10 and make it go rather fast. So usually all of the stepping problems occur with fast moving geometry or fast moving simulation in general. Alright, so let's say that from here, let's drop this into a pop net. Okay, so drop a pop network from here, and let's step inside, and I'll just disable the guide, and maybe go to the birth tab, and let's add another extra set of, let's multiply this by 10, so 50,000, and let's use a life expectancy of 1 because we don't really need this to last that much. So let's press play. So this will be the first case. What's basically happening is that we are taking every frame, and then if I move forward by using my keyboard arrows, if I move forward 1 frame, then we are spawning emission right where the geometry is, basically. Okay, so the first way that we fix this is there is a built-in option in the birth tab, in the source, in the pop source node, so in the birth tab. If we go to interpolate source and we set this to back and let's resimulate, we can see that already there is some interpolation. So if I go forward 1 frame, we can see that we have successfully sort of got rid of the stepping. And simply what's happening here is if I go forward a few frames, let's maybe go up and let's also template our geometry. So if I go on frame 3 and then I go on frame 4, it's basically going to blend the points from frame 3 to 4 by using a random value based on the ID. So what this does essentially is if I were to drop a scatter from here for my sphere, and let's just disable relax iteration and scatter a bunch of points. So if I were to time shift this scatter and move this time shift, let's add 1 frame to this, so let's move it forward in time 1 frame. This operation here simply blends between the frames. So if I drop down a blend here, blend shapes, and plug my second input here, if I increase this blend value, what this will do is this blend value will be randomized for each point. So some points will receive 0.1, some will receive 0.5, and so because this is randomized, it will fill the gaps between the frames. Okay, and let's go back inside, let's delete this, let's go back inside, and by default this interpolation method is set to match topology, so it will look at where my sphere was on one of these frames. So it will look at where my sphere was here based on the topology, and then it will look at where the sphere is on the next frame, and again based on the topology it will spread all the points between them. And the other method, if we go back inside, is going to be, so the other interpolation method is going to be by using the point velocity. And let's go up, so let's add the velocity to this because we currently do not have the velocity. Let's compute this by dropping down a trail node, and let's set the result type to compute velocity. And if we look at our vectors, we can see now that we do have the velocity. So now if I go inside the popnet, if I press play, we can see that we have a problem, and that's because the velocity is inherited by the particles and it's being used to push the particles away. So we have to go back inside here, and inside the attributes we will have to set this inherit velocity to 0. So now it will use the velocity to create this random blend for each particle. And it kind of works the same way. So some problems that can occur here is you might have changing topology from frame to frame. So if I go to the sphere and I add let's also add a mountain to this. So we'll just add some noise, and let's also go to animation and let's animate this noise. So this is the result. And let's maybe add another attribute noise to this, and let's maybe add some noise to the color. So let's maybe use a float. So this will make it black and white essentially. And let's use 0 centered here and also animate this noise. And maybe I'll change the offset. Alright, and let's make this topology. So we currently have the same set of points for each frame. Let's maybe delete some of these based on this color. So I will drop down let's drop down a delete node. And let's use delete by expression, and let's place CDX greater than 0. And let's go here and let's maybe delete non-selected. Okay, so we can see now that let's maybe press D and go to background and make this light. So now we have inconsistent, we can see that we are working with different points on each frame. So we have inconsistent geometry now. So what will happen now is if I go back here, let's maybe press D, set this to dark. If I go back here, this might not be as noticeable, but let's maybe increase the birthing. Let's increase the birth rate. Let's add another 0 here. Okay, so here we have it, and we can see that there is we are starting to receive some stepping here, and this is because when we compute the velocity, let's maybe take a look here. If I turn on my velocity, so because we are adding and deleting new points for each frame, some of these points will not find their matching partner in order to calculate this velocity. So some of these velocities that point in this weird direction are the points that no longer exist on the next frame. So as I play this, we can see that we have a lot of weird velocities that point in kind of random ways. And this will be the same if I change this to use match topology. So because our topology is inconsistent from one frame to another, this of course will give us the same nasty result. So in most cases I will use the point velocity method, and what we can do here is we can actually make our velocities be straight. So the way that we can do this is we can drop down from this transform. I will pack this and I will turn this into a point. So I will drop down and add, and we want to delete geometry but keep the point. So we just have one point here, and we will calculate the velocity on just this single point. So I will maybe duplicate this trail. Alright, so we have the velocity for one point, for this point here, and now we can do an attribute transfer on our original geometry, and we will transfer the velocity from this single point. Okay, so now as a result, all of these points will have the same velocity basically that this single point has. Okay, so if I preview a few frames, we can see now that the points have the correct quote-unquote velocity. So if I go to my PubNet now, we can see this kind of fixes it. So we have the correct interpolation of the points. The problem here is we can still see some stepping here, and this is because we are changing the source every frame. So this problem is occurring here. So for example, on this frame we might have particles that go from here, and then the second frame we cut this abruptly and then they start going from here. So there will be some inconsistencies here. So in this case, what we will have to do, unfortunately, is we will have to go to the simulation and increase the substeps. So maybe let's use a value of 3 and see what happens. So let's press play. Alright, and here is another problem that happens. This is really not the result that we are after. And when you get weird errors like this, the first thing that you should do is check your source. So if I go, before we add this into the PubNet, let's check our source. And what we can do from here is I will drop down a time shift, and I will just use this time shift to check if this source is interpolating correctly between each frame. So what I mean by this is I will go to this time shift, I will Control Shift to remove this expression here, and I will uncheck integer frames. And now what I can do is if I increment this frame number by smaller values, so let's maybe try 0.1, so we can see that as I increase this value, this source isn't moving. So it's kind of jumping between frames. And we can also do the same thing here. So let's maybe, if you don't want to use this time shift method, you can right click the global animation options here, and you can remove integer frame values here. And then if you scroll your timeline, you can scroll in a kind of float value, so it will no longer snap from one integer frame to the next one. And we can see that we have no interpolation here. And this is because if we go all the way back up here to where we create our rotation, this expression is using $F, and this means that only the integer values will be considered. So usually for simulations, if you want to use this expression, you will have to use the other form of this frame function, which is FF. So now this will no longer return the integer value of the frames, it will return the actual frame value. So for example, here we can see we have 8.836, so it will use this value instead. So now as I scroll my timeline, we can see that we have this really nice smooth interpolation. Let's maybe go back here and turn on integer frames. So this was the problem here with the $F expression, and now our substeps will have that extra information needed to create this smooth blending result. And now we can see that that problem was pretty much corrected. So like I said, you only want to increase the substeps only as a last result, and the only reason we did this here is because we have this really weird topology on the source. And I don't think that this is the kind of sourcing that you will often encounter, but yeah, sometimes you will have to increase the substeps. But like I said, only as a last resort. And remember that whenever you want to use multiple substeps and you get a weird result, always check your sources. So you can drop down a time shift, remove integer frames and the expression, and just increment this and see if it interpolates smoothly between non-integer frames. Alright, so this will be the first example. The second example is, let's maybe grab another sphere here, move it to the side. So let's drop down a popnet, and let's say that we want to make some calculations directly inside of this popnet. Let's remove the guides and increase the birth year and life expectancy to 1. So I will just simply add a pop VOP, and let's just move these straight up. So let's add a parameter, and I will set this to be a vector, and let's give this a value of 10 on the Y and plug this directly into the V. So if I press play, we can see that we immediately have some stepping. So we are moving a value of 10 for each frame, and since this is moving pretty fast, we encounter this stepping. So a very easy way to fix this is we just want to randomize this velocity for each particle. So from the ID, I will drop down a random, and we will just multiply this velocity by the random from here. So now if I press play, all of these will have a random velocity, and as a result, it will fill in the gaps between the frames. So this is quite a simple fix. So whenever you want to control the velocity through a pop VOP or a pop wrangle or stuff like that, you will just create a random value for each ID and then multiply whatever you are doing here with this random value. So this is another example. And finally, let's also look at some particle advection. And I have a very simple setup here. I have the same sphere. We add some noise, and this noise is also exported to a density attribute, and then we rasterize this density, and then all of this is plugged inside a DOP network, which is running a pyrosolver sparse with a couple of turbulence nodes, and we have the density here. So the simulation looks something like this. And we are importing the velocity field outside in the sublevel, so with this DOP import fields, and then we can now use it inside a simulation. So the same sphere here, let's maybe place this over to the side, and I will just add a pop net here. And inside here, let's turn off the guide and increase the birth rate and maybe do a life expectancy of 1. And I will drop down a pop advect by volumes. And I will use this velocity that we created from the smoke. So I will grab this, Control C, and I will place this here. And by default, it's looking for the field name vel, which is what we want. And we will say update position, final velocity and trace. So this will give the best results for the advection. And let's press play and see what we get. So right off the bat, we have some stepping over here that is pretty clear to see. Let's go back and let's also inherit the noise from this, or rather the color from this, from where we set up the density. So it might be easier to see the stepping. Okay, so here is the problem. So if we go frame by frame, we can see that the particles are being pushed, and because the smoke is moving fast, it's creating this weird stepping issue here. So this is the most common place that you see people just straight off the bat start increasing the substeps, and this kind of works. And if I increase the substeps to 5, you can see that this kind of works, but we still have a little bit of a stepping effect. Now this is hardly noticeable and it might work, but instead of just increasing the substeps, so the problem in this case occurs really right at the beginning, so maybe in the first half second, because later in the simulation when the smoke starts to spread out, we really have a lot more velocity information to work with, and we only need to blend the result right in the beginning of our simulation. So what we can do here is we can go inside and we can turn on this use of expression, and I will scale this velocity scale by the age of the particles. So I will say vel scale, which is the parameter name of the velocity scale here, and I will just say multiply equals fit, and we want to fit this using the age, so I will set at age, and let's maybe fit this from 0.1 to 0.3. So this is in seconds. And let's fit this from 0 to 1, or actually let's use 0 here for my first age. So right when they start to spawn, over a duration of 0.3 seconds, they will go from 0 to 1. So as a result, if I look frame by frame, right in the beginning the particles will not receive the full force of our smoke, and it will blend over a third of a second, so maybe up until frame 8. And now since they are blended in the beginning of the simulation, they will sort of maintain this relationship as they get advected further by the smoke. So if I just play the simulation, we are really just changing what's happening right in the beginning of the simulation, and then everything else will be advected in the same way by the smoke, and we get rid of all of the stepping. So we can see that we are only using 1 substeps here, and this will be a lot faster, and really we can see that we have almost entirely no stepping at all by doing this. Now if you were to go back inside and instead of using this fit method, you would use, maybe you would do the same thing that we did with the pop VOP thing, which is the randomize thing. So if you were to randomize this by the value of the ID, the result isn't really what you want, so it won't follow the smoke that accurately, but we can see that we do get rid of all of that ugly stepping. And this is something that you might want to do in some cases. So maybe when you want to, this sort of diffuses the whole smoke simulation. So maybe this will be helpful if you don't really want as much detail in your advection. So this is also something that you can do, but usually I will do the fit age method in these cases. So finally I will disable the expression here, and let's create the ugly stepping result. And let's maybe use a little bit more particles, so I will add another one here, just so our stepping is noticeable. And what you can do as a final method, if nothing else works, you can just brute force the blending after the simulation is done. So this will be after we cache the particles. Outside of the simulation we can do our we can do our own interpolation between frames. So we will need, let's drop this into an attribute wrangle, and we will want to time shift our particles, and you can either time shift them one frame forward or one frame behind. It works either way. Let's just do one frame behind. So I'll set this expression to $f -1, and I will place this as my second input. Alright, so this will be our present simulation, and this will be our past simulations. So let's go inside this attribute wrangle, and the problem here is that we can't really just grab the position from our past particles and just simply blend them. So if I were to let's do a variable vector, and I will name this pause, and we just want to grab the position of the points from my second input, so the past particles. So let's do a point expression, and let's look at the second input, so 1. Let's look for p, and if we run this on ptnum, the problem will be that the present particles and the past particles do not have a consistent point number. So we can see here that we have for the present particles 1.5 million points, and for the past particles we only have 1,400,000 points. So this ptnum will not match. And basically what happens in general is for particles that each frame we are adding new points and deleting old points. So this will mean that the point number changes from frame to frame. So we have concluded that we can't really use this ptnum value here. What's consistent between each frame is going to be the ID. So if I were to place the ID here instead, this unfortunately also does not work, because the point expression is looking for a point number. So if I just simply place the ID here, if I were to go to any of these points, this point over here might have an ID of 50, but it will have a point number of 20,000. So if I put the value 50 here, it will look for the point number that has a value of 50, which might be a point all the way over here. So hopefully this makes sense. We can't really use this ID. What we have to do is we have to find the point number that has the same ID in our past particles as the same ID in our present particles, and we can use the find attribute val function for that. So before we set out to find the position for our particles in the past particles, let's first find the point number that we are looking for. So find attribute val will return the point number, so I will say that int, and I will name this point number pt, and I will say this is equal to find attribute val. And in between parentheses, first we will look at our past particles. So the second input here, which is 1, this will be a point attribute, and the name of this point attribute will be ID. And we want to match this ID with our current ID, so the value will be at ID. So this whole expression here will find the point number of our past particles that have the same ID as our present particles. So now to grab the position, instead of using the ID here, we will use this pt integer that we just found out with our find attribute val function. And we can now create a blend between the frames. So we can say that at p equals lerp, and we will blend between the current position and this new position that we found. And let's create a float here, float blend, and let's first set this to be just a simple float channel. So I will say ch, and I will name this blend, and then I can place this blend float here. Okay, so let me just illustrate how this will work. If I now increase this to 1, if you ignore this weird thing that's happening here for a second and just look at the rest of the particles, we can see that we are moving the particles between the frames. So what's happening over here with this weird thing, that's we can see that a set of points are being translated right to the origin of our scene. And this is happening because if we look at our present particles, these present particles have some points that are not yet existing in our past particles. So we have a set of points on our present particles that can't find their matching partners in the past particles. So to fix this, we sort of have to ignore the points that don't have a matching ID. And the way this function works is if this findAttribute_val function does not find their matching IDs, it will return a value of -1. So here I can see before the lerp, I can say that if this PT that we find is not equal to -1, only then do our blending. Alright, so now this will fix it. We are simply ignoring the points that don't find their match in the past particles. Now instead of using this channel to blend this, I will blend this by using a random number for all of the IDs. So I will just say that our blend will be random at ID. So here we go, and this is the brute force method. And if I turn this on and off, we can see that this gets rid of the stepping. So we can see that the result is a little bit sparse. So I really wouldn't recommend using this unless you have tried all the other methods and this is the only method that you have left. So I will put up this file for download, so check the link in the description and you can check this file if you want. So this is everything I wanted to cover for this video, and I'll see you next time.